The uncertainty principle is one of the classic examples of quantum physics. It's a reflection of the fact that these particles are really waves. They're probability waves, but they're waves. And so they have the same features of waves. If they're described by a wave, if anything is described by a wave, then there's going to be an uncertainty in its position and momentum. And that's true for an electron. So when you confine it so you know exactly where its position is, that means you're losing information about its momentum. If you measure its momentum really, really well, that means you have to be losing information about its position. So in this case, you've done some sort of experiment and measured the velocity of an electron to be 3.4 plus or minus 0.1 times 10 to the 6 meters per second. So the 0.1 represents our uncertainty in the velocity. So it's 0.1 times 10 to the 6th, otherwise known as 10 to the 5 meters per second. So 100,000 meters per second. We know the velocity within about 100,000 meters per second. That uncertainty in the velocity can be translated into the uncertainty in the momentum. So that's what sigma p is, the uncertainty in the momentum. And we get that by taking the mass of the electron and multiplying by the uncertainty in the velocity. When you do that out, you get this number, and this number is the uncertainty in the momentum. The momentum must be within that range. So what does this mean? Well, it means that we have a certain precision to our momentum measurement that is going to lead to a certain precision in our position measurement. If we were to try to state exactly where the electron was, if we try to localize where it is. And that's given by the uncertainty principle. So we have the uncertainty principle written here. Sigma x is uncertainty in position, sigma p, uncertainty in momentum. That product always has to be greater than or equal to Planck's constant divided by 4 pi. Now, when you rearrange this, because what we're interested in now is the uncertainty in position, you get that the uncertainty position is greater than or equal to Planck's constant over 4 pi times the uncertainty in momentum. And plugging those numbers in, we find that the uncertainty in position is greater than or equal to 5.8 angstroms, or about 6 angstroms. Putting it all together, by measuring the velocity to this level of precision, we are limiting how well we can localize where the electron is. So we can tell what its velocity is within about 100,000 meters per second. But by knowing that, to that level of precision, we can only say where it is within about 6 angstroms. Okay. If we were to localize its velocity, and say we designed a slightly better experiment where we could measure the velocity by a couple order of magnitudes better. So that would mean we'd be lowering sigma p. If we lowered sigma p, we'd be increasing this, and we'd be increasing the uncertainty in where the electron was. This is not something you can get around. It's a basic rule of nature that you can't have perfect information on where the quantum particle is and how it's moving. The better you know one, the worse you have to know the other one. That's the essence of the uncertainty principle.